Hello everybody, this is Introduction to Analog and Digital Communication book. In this course, Communication System, I am Amar Abdul Bari with Nearest University. I will continue on the analog communication. Previously we speak about the AM modulation, amplitude modulation, and its successives. So we speak about double sideband suppressed carrier, the single sideband, and vestigial sideband. Today we will continue to next chapter with angle modulation. Angle modulation includes AM, not AM modulation, the FM and BM modulation. FM modulation, frequency modulation, and phase modulation, both of them are changing or modulating the phase or what is inside the carrier here. AM is about changing the amplitude. That's why it's named amplitude modulation. Now there is a general name, angle modulation. Let's see it how it's derived and how we get the frequency modulation and the phase modulation. Okay. Now assume that this is S of t, AC cosine theta I. Whatever here is the theta I. This is the angle of the cosine. Now this angle, usually we put number in calculus, but here we will change it accordingly. We will change it according to specific parameters. So we can modulate according to a modulating signal. So now here the average frequency in hertz is f of t delta t. It's t plus delta t minus theta I over 2 pi delta t. Here it is changed from t to delta t. So this is the integration, the differentiation of the theta I. So the instantaneous frequency is you take the limit of the delta t to which reach or limited to the 0. When it's go to 0, it's 1 over 2 pi delta the differentiation of theta I t over delta t. If you remember this x of delta x minus x over 2 by x or over x delta x. So this is how you get the instantaneous frequency and how you get the average frequency in hertz. So what is theta I? Theta I is 2 pi fct plus phi c. Here I will speak about some mathematical side of the frequency modulation. However, it's very easy to make it in or to understand it or visualize it, but to able to implement it hardware in the transmitter and receiver, you have to get some knowledge about the concept, the mathematical or theoretical concept. Okay. Now the phase modulation. In the phase modulation, it's the change of the phase. So 2 pi fct plus kb of t. So this is theta I. In the frequency modulation, you change the frequency. So fi t, it's fc plus k fm of t, each over a assume or this is all definitions that we write it by hand, so we can define the frequency modulation. So the difference here is 2 pi fct, the carrier frequency, plus integration of the m of t, the modulated signal, multiplied by 2 pi kf it's or kb, it's just a sensitivity, a frequency modulation sensitivity. Okay, so this is the theta is 2 pi fct plus 2 pi kf. This is theta. Here he modulate the we take the integration of the fi of t. And if I is fc, fc is not something, you can take the integration by multiply by t, and here you have to take the integration over m of t. So this is very easy to go through. Now this is a basic definition in angle modulation, the same idea that I write before for phase modulation and for frequency modulation. And as I said, kb, kf is frequency and phase factor sensitivities. Properties of angle modulated signal is the average power is a constant 1 over 2 AC square, the amplitude square. The non-linearity of the modulation, because you change on side cosines. So if you take the summation of the input, you can't take the summation of the output. You can take is here m of t, m1 plus m2. If you put it inside here cosine, if you take s1 and s2 as the output, you can't assume that st is equal s1 plus st. Here this is s1 st. Here if you take the summation, you can't get to this equation. That's why it is non-linearity. See, here is the signal, the carrier wave. This is the modulating wave. This is the AM wave, the AM amplitude modulation. As you see, we change the amplitude as the change happened in the signal, the message signal. Here this is phase modulation. It change the phase according the phase, not the frequency. The frequency is the same, but we change the phase whenever there is a change in the signal. So we can get our signal directly. Here is the change is in the frequency itself. Here the frequency modulated signal. So for example, there is here increase in the voltage, so there is a lower frequency. When it's go to the other side, or the different, when it's go to up, it's the increase in frequency, and lower frequency, increase in frequency, lowering the frequency. So the frequency, it's a number, it changes according to the changes in the message signal. So you changed so you have to follow the changes here. What's happening here, you have to follow. You have to follow the change in the slope of the signal. If it is highering, lowering, going down, going up, the change in a signal over time, this is the meaning of the integration or the differentiation. So to able to express or represent the frequency modulation, you have to express it or represent it using the integration and the operation and reverse the differentiation. So you should follow the change in in both of them. Here you don't, in the AM you don't follow the change, you just follow the envelope. Here you just put the signal in the top of the carrier in the AM modulation. So the other probability is the irregularity of the zero crossing. So the zero crossing meaning then where the amplitude change from positive to negative, or the other way. So there is irregularity because of the non-linearity characteristic. You don't know when it will happen or crossing the zero. Okay, so another property is the visualization is very difficult, or you have a difficult because of the attribute, because of the non-linearity. There is a trade-off of the frequency, because you increase the bandwidth of the transmission because you use multiple frequencies. but you improve the noise performance, because you don't have to change in the amplitude. The amplitude is the same, but you change in the frequency, so nothing is changed, or the noise, it doesn't have much effective, especially the additive noise, which is added to the amplitude. Okay, now let's see here. Here is giving an example of m of t, the signal at, where is t higher than or equal to 0 and 0 otherwise. So this is m of t. Here this is m of t. Here is the phased, the modulating signal or the carrier signal. Here is the phase modulating signal. You see here, when it is 0, there is a signal that's go up and down directly. When it is going up in the frequency here, the change here, it doesn't appear directly. The change is in the phase. So the signal, it's not beginning actually in the beginning of the signal of the 0 here. That's why we say that the visualization is not it's not easy to understand the concept. In the frequency is more understandable. When there is 0, there is a very low frequency. When it is go up, it is follows the change, and there is a change here, a slope, so it go up in the frequency, higher the frequency, higher the frequency, higher the frequency. If it is lower, then it will return back and go up and down. So it is there is no discontinuity in the going from one frequency to another. It's follow the change in the m of t. It's expressing this rate of a change in the frequency. Okay, so let's see here. The relationship between the phase modulation and FM modulation. And the FM modulation can be generated by integrating the message signal with respect to t, then go to a phase modulation. This is the FM. The BM can be generated by differentiating the m of t with respect to t, then the input goes to a frequency modulator. This can be so this is the message signal here, or the modulating wave, with same name or different name for the same thing. Integrator, then a phase modulator, and you get the FM. This is a relation between both of them. You can get the modulator to the signal to phase modulator to get BM, but if you input your signal to an integrator, you take the integration of the signal, then you can go to a phase modulator and then FM. Of course, we will get later what is inside here. So this is the relation between both of them. Now let's see narrowband frequency. Narrowband meaning that a single tone modulation that produce narrowband FM. So assume that m of t is equal to am cosine 2 by fm of t. This is the frequency of the message signal. The fi, if you remember, the fi is equal to fc plus kf am cosine. We just put the m of t here, and he makes some assumption kf multiplied by am. He make it as delta f here. So delta f over fm here. Theta I of t here. Theta I think there is integration. You should remember this equation, or use it to understand what's happening. Here we make this fi, then we take the theta I. Theta I is taking the integration. So you get in one side 2 by fct, and the other side you take the integration of the m of t. M of t here is cosine, so if you take the integration, then it will be sine. Okay, so the here delta f over fm, we can name it as a phase deviation. This is the frequency deviation, this is the modulation index, this is the phase deviation. So theta I of t is equal to 2 by f of ct plus beta sine 2 by fmt. I think until now everything is clear if you go through mathematically. Now fm wave, you can after that we take theta I, we put it into the cosine. So AC cosine 2 by fct plus beta sine, this is what we have here, this is the theta I. Then we will use this from this equation from the trigonometry, cosine A plus B, cosine A B sine sine. So you apply that to this equation. So cosine 2 by fct, cosine sine, this equation minus sine sine. Okay, now this is the full equation for s of t. Now if this is the modulation, he will make some assumptions. Now this is just assumption to reduce the complexity of this equation. So the modulation index, where is the modulation f of m? If the modulation index is very small compared to 1 radian, so the approximation, we can make some approximation. We can use this cosine beta sine 2 by fmt as equal to 1, and sine this, because this is very complex, sine beta sine is equal to the what is inside here, so it is beta sine. So you can take this assumption and put it here. So this is 1, so the left is AC cosine 2 by fct, minus here it is, you just remove this sign from outside, so it is AC sine 2 by fct multiplied by sine 2 by fmt. Okay, so here we have the harmonic distortion around the fc of fm here. This is the modulation. So this is the block diagram. I think we should go more. Yes, here he want to generate this equation 4.5. So I want to generate this equation, so I will generate the signal, the carrier signal here. This is one. So I take the modulation, I put it to integrator, I take the product integrator. Why? Because this integration, where is in the first signal, we take the integration here, this is the integration. Okay, so I make a product modulator, I make the carrier wave here, the oscillator, cosine 2 by fct AC plus, so this is this one minus beta AC sine sine. So sine, so I make a phase shift of the sine here, phase shift to get this sine. I multiplied by the sine of the fm and multiplied by the beta theta I AC. Okay, so this is the product modulator here, minus, so I get the narrowband fm. Okay, this is how I can get or generate the narrowband fm. Now he may re-express it again, this equation sine sine. You can express it as cosine plus and minus two angles. So cosine fc plus fm, cosine fc minus fm here, and this is the carrier again. So this signal is 4.18. If you remember from previous lecture, or the lecture before that, AM modulation is the AM modulation, not the suppressed carrier or double sideband. Is there is a carrier wave, there is two cosine and sine, cosine to the signal is around the carrier, upper sideband and lower sideband. So but here there is mu. So the basic difference only is this, is you see here, the basic difference here is the algebraic sign of the lower sideband between the AM and narrowband FM. Okay, so they take the same transmission bandwidths essentially. Okay, now this is not related, I will skip that. Okay, So I will stop here. Next lecture I will speak about the wide band frequency modulator and how we can generate the FM and demodulate the modulation and demodulation of the FM. Okay, thank you for listening.